Bonjour. As you know, the Geopolymer camp has been cancelled, but it is a well-established tradition that I present what I call the state of the geopolymer research and development for each year. This has been our preliminary program with 4 focused sessions. In the first focus session titled Manufacture of Metakaolin without calcination at 700-800 degrees C, Mechanico-chemical processing at room temperature, I will present a small summary on this keynote. In the second session, in the industrial applications, we had the focused session planned titled Fiber Reinforced Geopolymer Composite, and I will also present a small summary of this keynote. Then on Wednesday, at the fourth session dedicated to the buildings applications and eco-construction and CO2 mitigation, we had the focus session, very important, titled Fly Ash is a Climate Killer. Replace fly ash with ferro-sialate-based cement. And in the session dedicated to Geopolymer Science applied to archaeology, I wanted to include some examples that are provided by ancient Roman cement and concrete that are based on red colonitic Metakaolin. So, the state of the geopolymer for this year comprises 4 parts: Geopolymer Science, Geopolymer Technologies, Geopolymer Cement and Concrete, and Geopolymer and Archaeology. Let's start with Geopolymer Science. In April this year, we released the 5th edition of my book, Geopolymer Chemistry and Applications. In addition to the numerous updates, this 5th edition adds 2 new chapters. Chapter 11 on Ferro-sialate Geopolymers, and Chapter 21, How to Quantify and Develop Geopolymer Formulae. This last new chapter details how to select raw materials, how to calculate a formula, and describe the process method for optimal results, all in a very pragmatic way. At the beginning of the first Geopolymer camp, 11 years ago, I listed the various research topics that had to be carried out in order to progress in geopolymer science. First, polymeric character of geopolymer. Number 2, polysiloxanate, that are the soluble silicates. Number 3, Metakaolin MK750-based geopolymer. And you see that this one is in blue. The ones that are in blue means that they will be discussed during this keynote. Calcium-based geopolymer, rock-based geopolymer, silica-based geopolymer, fly ash-based geopolymer, phosphate-based geopolymer, both in blue, organic mineral geopolymer, long-term durability, we will come also to this, Geopolymer Fiber Composites, Geopolymer in ceramic processing, the manufacture of geopolymer cement with fly ash, that is the big discussion on that topic, Geopolymer Concrete, materials for radioactive waste, particles and gas pollution, and number 16, 3D printing. So let's start with the first one, which is number 3, Metakaolin MK750 based geopolymer. We have 3 topics, 3A, 3B, and 3C. We start with the 3A, which is dedicated to the keynote, Mechano-chemistry of rock materials for the industrial production of new geopolymeric cement by Piero Ticcioli from the Istituto di Metodologie Chimiche, Rome, Italy. I start to read the abstract. In this chapter, mechanochemical processing, that is, grinding technique of kaolin clays to produce metakaolin for the synthesis of SiAl geopolymers is proposed as an alternative process to replace thermal treatments performed at 650-850 degrees C. Results obtained show that the mechanochemical process is also suitable to make low-cost blended SiAl rock-based geopolymers. The compatibility of mechanochemistry with industrial production was investigated by building a prototype milling system that was tested in a small industrial facility producing zeolites from industrial waste. The degree of automation allowed the prototype to work unattended for 10 months. Based on the results obtained from these tests, a milling system for a full-scale production of mechanochemically activated rock materials was designed and its performances analyzed. This type of development started years ago. I have our friend Kenneth Mackenzie from New Zealand, who, with his group, published in 2007 the first result, but on the lab scale. And here we have the first pilot and industrial scale applications for this system. They have investigated the results of mechanochemistry on raw kaolin clay in order to manufacture metakaolin, and the investigation tool is nuclear magnetic resonance spectroscopy and essentially aluminum. Here we have the resonance of the aluminum of the raw kaolin clay. Here we have the resonance for the same for the clay that has been transformed into metakaolin with the calcination at 650 degrees C during 2 hours. And this is the result with the mechanochemistry processing during grinding 30 minutes at very fast speed at 1,500 rotations per minute with well-defined AL4, AL5, and AL6 resonances. I consider that this technology is very appropriate in manufacturing of rock-based ferro-sialate geopolymer cement. These are the type of geopolymers that I am strongly recommending now. And we come to these ferro-sialate geopolymers. It is described in chapter 11 in my book, Geopolymer Chemistry and Applications. This is a new chapter. It comprises the structure iron, Fa, O, Si, O, AlO, ferro-sialate, which has part of the aluminum partially replaced by iron atoms. So it has been also put in our Geopolymer Institute library as a technical paper number 27 that can maybe downloaded for free. I received a paper that is illustrating this new technology, and it came from Thailand, titled Superior Properties and Structural Analysis of Geopolymer Synthesized from Red Clay. So the group compared 5 different clay, one white lampang kaolin and 4 other one, and they compared these clays with a very different Fa2O3 content. The lampang kaolin has only 0.8% Fa2O3, whereas the Chiang Mai red clay has a 26% 0.4%, so it is a high amount of iron oxide in it, and the others between 7 and 3%. They calcined the clay and transformed them into a regular sodium geopolymer, cured at room temperature after 28 days. They got the following mechanical resistance, compressive strength. Check my red clay, the one that has more than 26% Fe2O3, 38 MPa compressive strength. The Metakaolin, the white one, 26, and the others 18, 21, and 8. Same for the flexural strength, 3-point bending strength, 11.40 MPa, and the others only 7,666, which demonstrate that, in fact, the high content of Fe2O3 of iron oxide from the type Fa3+ is providing a very interesting raw material for geopolymer cement applications. Number 3C, we put the standard for testing Metakaolin. We had a special session last year on that topic, and it is in the chapter 8 of my book, and also chapter 9, dedicated to quality control. There is also a paper that we wrote, this paper number 26, wrote by Ralph Davidovits, Christine Pelgris, and myself. That is, it is a work that has been performed in our lab here in Saint-Quentin. It comprises a thermal element. We are measuring the exothermic behavior of the geopolymerization during curing at 80 degrees C. The samples were prepared in the following way. The reactive mixture is made of 100 grams of potassium silicate or sodium silicate solution with molecular ratio of the silicate 1.7, to which is added 60 grams of Metakaolin, and this has been mixed for 10 minutes at 20 degrees C, and then the hardening is done in plastic containers like this one. These are very simple containers that are covered with a lid, and here we have the thermal element coming through the walls outside and measurement with the device. The oven is at 80 degrees C. The temperature is measured with electronic devices or simple thermometer. There's no problem. Hardening sample must be covered in order to avoid any drying of the surface during the setting. What we get depends on the alkali that has been used. For potassium-based geopolymer, we got an exothermal peak after 27 minutes that reached 103 degrees C, whereas for sodium-based geopolymer, we got it after 35 minutes, that is later, with a higher peak at 190 degrees C. It depends also on the calcination method. It is either flash or rotary calcination, so we take the same geological sample, calcined at 700 degrees C, and you see that the flash system, this is the M1200, reaches after 22 minutes the thermal peak at 103 degrees C, whereas the one that has been calcined in a rotary oven, that is the M1000 from Archaeology, reaches after only 34 minutes at 100 degrees C Celsius peak temperature. Here you have tested the 10 commercial Metakaolins that we can get here in France. So we get Archaeology 1000 M200, Metastar 501, Pause, Metaver, Metamax, Archaeology, and so forth. And we have here the blank sample, the time, and the temperature reached in the samples, and you see that they are different. And we have the flash that reacts very fast, and then the high strength regular Metakaolin, and then others that are reacting slower. Number 8, research topics number 8, phosphate-based geopolymer. There are two developments. The first is the exothermicity. The phosphate-based geopolymer is carried out with the reaction of Metakaolin and phosphoric acid. And we performed the same testing as we had just shown for the alkaline medium reaction with Metakaolin and potassium silicate or sodium silicate. And as you see, the behavior is absolutely identical. It is similar with the same exothermic peaks depending on the curing time and curing temperature. The second development is based on one question that is raised by chemists is the following. What type of geopolymer unit do we get when reacting Metakaolin with phosphoric acid? The discussion is around the fact, do we get the sequence Si, O, P, O, Al, O, silico-phospho-aluminate sequence, as it is written in several scientific papers, or, like what I am claiming, do we have what I call a solid solution that involves SiO2 silicate plus aluminum phosphate separately? Well, the answer has been provided last year by a group from the École Nationale d'Ingénieurs de Sfax, University of Sfax in Tunisia, structural characterization of phosphate-based geopolymer. And then under SEM, they discovered that we effectively have two geopolymeric units, geopolymeric network based on SiO2 units here, and the second geopolymeric network based on ALOP units. So the ALOP unit, aluminum phosphate unit, is in solid solution with the SiO2, which could be SiO2 silicate or perhaps SiOP silicon phosphate, but I am doubting that it is silicon phosphate because this requires higher curing temperatures. So the answer to the questions that had been raised, do we have SiOP or ALO sequence, is no. Research topic number 10, long-term durability. It is part of chapter 18, that is the chapter 17 in the previous editions. And I have always claimed that ancient Roman cement is providing a good example on long-term durability of geopolymer. These are archaeological analogues for geopolymer cement. You'll find also on our Geopolymer Institute internet site pages dedicated to that topic, titled Archaeological Analogues, Roman Cement and Long-Term Stability of Geopolymeric Materials, where I'm claiming that, in fact, in the good Roman cement, there is the presence of a geopolymeric network. Well, submitted 29th January 2020, there is here a research paper, the importance of the ultra-alkaline volcanic nature of the raw materials to the ductility of Roman marine concrete. The authors are Jackson McFarlane and his group from Stanford Research Laboratory, Stanford University, and Department of Civil Engineering from University of California, Berkeley. I start reading the abstract. Ancient Roman-era concrete is the iconic embodiment of long-term physico-chemical resilience. We investigated tomographic imaging of macroscopic mechanical stressing with structural microscopy and chemical spectroscopy on Roman marine concrete from ancient harbors in Italy and the one in Israel that is called Caesarea. Stress-strain measurements revealed that Roman marine concrete creeps and exhibits a ductile deformation mode. The permeability of specimens from Italy were found to be low due to increased matrix aggregate bonding. Structural and chemical imaging shows the presence of well-developed sulfur-rich fibrous minerals that are intertwined and embedded in a crossbred matrix having the chemical traits of both a calcium aluminum silicate hydrate, or CSH, and a geopolymer. This latter, that is sodium-based geopolymer, likely reflects the ultra-alkaline volcanic nature of the primary source materials. So if we look at the X-ray maps of the distributions of calcium, sodium, and aluminum, and this is what we get. The blue arrow shows the calcium-rich region, for example, CSH type or carbonated lime, like here. Blue, this is calcium-rich, whereas the white arrow shows NaSiAl-rich geopolymer. Here, for calcium, we see that here we don't have any calcium. We don't have any calcium, but for Na and Si at the same places, we have sodium, we have aluminum, and so forth, and so forth. So we have, with inside the CSH calcium-rich region, the production of a geopolymeric network. Number 11, Geopolymer Fiber Composites. This is also described in the chapter 23 of my book, and it was chapter 21 in previous editions. We had been involved in a research project that had been sponsored by the American Federal Aviation Administration more than 20 years ago. In 1997, we published in the journal Fire and Materials the result of our study on fire-resistant aluminosilicate composites. The partners of this research project were Richard Lyon from the FAA, P.N. Balaguru from Rutgers University, Usman Sorasia from US Navy, and myself and my brother Michel from Geopolymer. This has been published in Fire and Materials, and it is in the library of the Geopolymer Institute, and it was technical paper number 1 that we put in 1997 online. And since that date, it has been downloaded more than 11,700 times. It is the investigation on fire-resistant panel made out of geopolymer carbon composite. The project lasted from 1994 to 2000, part of the aircraft cabin safety project, and the target is giving survivors more time to escape in case of a fire. What has been investigated is what is called the flashover. Flashover is a phenomenon unique to aircraft cabin fires. Fumes accumulate at the ceiling and self-ignite without any previous contact with flame. This is the graph that shows the behavior of various organic resin, organic-based composites with geopolymer. We have here the time to flash over, that is the time the material needs to self-ignite. The regular thermoset self-ignite at 12 minutes. Phenolics at 19 minutes. Geopolymer will never self-ignite, infinite time. Our project was stopped in 2001 because of the tragedy that happened in New York at the World Trade Centers, and the FAA put the project on hold because they could not afford to ask the American Airlines to use this new type of material because they were all financially bankrupt. The project was resumed in 2015 by a project sponsored by the European Union and titled Future Sky Safety, and this has been performed by the Czech Aerospace Research Center in Prague, in the Czech Republic. Here are the results. They have made the prototype that we wanted to also manufacture at the end of our project with the FAA in the US. That is a door. This is the door that has been subjected to the flame penetration test, and you see that the window has been filled with steel plates. Otherwise, they could not have been capable of running this type of test. This is a video showing how it behaves. These are the first results, and now I'll come to the video. It is now practically 20 to 25 years that Geopolymer carbon composite is marketed by our parent company, Pyromerol, in France, for advanced space aeronautical defense application. I show you a small video. So, this is a good introduction for the second topic, that is Geopolymer Technologies. I show you a brief survey of real technology that are at the pilot scale or commercialized. We have geopolymer binder, geopolymer resin, geopolymer paint, geopolymer coating, geopolymer grout, geopolymer foam, geopolymer cement, geopolymer concrete, geopolymer carbon composite, and geopolymer ceramics. For the silico-aluminate geopolymers, those obtained in the alkaline medium, the properties depends on the ratio SiAl. For SiAl 1:1 and SiAl 2:1, we have a strong, rigid, three-dimensional network, and the applications that are those of low CO2 cements and concrete, radioactive toxic weight encapsulation, bricks, ceramics, and regular fire protection. If we increase the ratio Si to Al 3:1, then we enter into the foundry equipments, tooling for titanium processing, some heat-resistant composite, more fire-resistant composite. If we increase the ratio SiAl higher than 3:1, we get a more polymeric character and enter in two-dimensional networking. We got sealant for the industry or toolings for SPF aluminum. And for higher SiAl ratio, but below 35:1, we manufacture the fire-resistant and heat-resistant fiber composites that are applied and marketed for racing cars and the likes, and are the subject of the study carried out for fire safety in cabin aircrafts. So we get here various applications. For example, Germany BASF, PCI Geofug, Geopolymer grout and binder. Milliken infrastructure in USA, geopolymer mortar systems and grouts for use in rehabilitation. In Germany, Inotech inorganic binder system, geopolymer binder for foundries. In Australia, Wagner's earth-friendly concrete, fly ash slag geopolymer concrete for infrastructure and building. Pyramidal system, France, high-tech, high-temperature structural geopolymer composite materials for automotive aircraft industries. Air Composites Ireland, heated geopolymer composite tooling for manufacture of large composite structures for aerospace, windmills, energy. Airbus France, aircraft conduit in geopolymer carbon composite. Schlumberger France, pumpable geopolymer formulation for oil-field application. Rockwool Australia, geopolymer rock wool briquettes used to recycle unused fibers. Scobern Germany, fireproof condensing chimney for hot gas exhaust made of geopolymer foam. Mataki Panel Singapore, precast geopolymer panel. Nucor China, geopolymer fireproof composite panels. Renka Russia, 3D printers for buildings. Corning USA, geopolymer ceramic composites for high temperature. Dow Chemical USA, geopolymer coating for organic polymer substrates. Oxo Sweden, composition for sustained drug delivery comprising geopolymer binder. Inomat Germany, fire-resistant geopolymer paint. Sinotech Germany, very resistant and acid-proof, rigid, anti-corrosive geopolymer coating for the protection of surfaces on metallic and mineral bases. Geopol Czech Republic, geopolymer binder for cores in foundries. Nova Lignum Netherlands, geopolymer composite siding and facade claddings. Nanovoltaic USA, nanoporous geopolymer composite for use in water treatment as an absorbent for the removal of arsenic. Allied Foam Tech Corp USA, Geofoam, geopolymer foam cement for lightweight and fireproof application. Völlner Germany, Geoseal, ready-to-use alkali silicates for geopolymer. Volnik Sklo, Czech Republic, geopolymer binder system for foundries. Polyurap Canada, Aeoncrete geopolymer concrete made out of mine tailings. Argeo Belgium, LTGS brick, low temperature geopolymeric setting. Reinforced concrete pipes in Australia, geopolymer concrete pipes. Watershed Materials USA, high-strength masonry with a low carbon footprint using natural mineral-based geopolymer. Bowers Industrial, 200 and 600 geopolymer concrete for acid-resistant application. Aqua Mineral Finland, solutions for water purification with patented geopolymer nitrogen removal absorbent. Amek Foster Wheeler, United Kingdom, Cial Matrix, a specialized geopolymer technique for encapsulating various radioactive waste streams. And in the same type of application, Lucide on United Kingdom, Midar encapsulation, immobilization of high hazard nuclear and chemical waste. Brazil, Wincrete decorative architectural geopolymer binder panels for inside and outside. And lastly, Neoterre France, geobiology applications. So, after geopolymer technology, we have now geopolymer cement and concrete. I have been shocked by this news, what I saw on the screen of my TV at the end of last year, December 2019. A continent is on fire. Both Australia and California have never experienced such an inferno. More and more citizens blame the climate change, the CO2 emissions responsible for this. Because of extreme heat and dryness climate, there is no rain. CO2 is essentially coming from coal burning in electrical power plants, and the coal burning in electrical power plant is increasing. Before 2012, I thought that the use of coal in electricity production would decrease. This has been the tendency at that time, but then I discovered that, in fact, since 2002, when we look at the world energy sources, since 2002, the use of coal has been increasing, and the trend is continuing. So I was wrong. We had more than 25% increase since 2002, and the governments of Australia, US, Russia, Brazil, China, India, Poland, South Africa, Germany, where coal mining and coal electricity power plants are significant industry and with powerful lobbies, are entrenched and want to stick to their coal policy and business. But do you know that the manufacture of 1 metric ton of coal fly ash is generating 33 metric tons of CO2 emission? Which means that all taken for granted ideas and promotional slogans about low CO2 cements based on coal fly ash are totally wrong. We should stop promoting fly ash-based cement. This has been overlooked by all experts, including United Nations environment experts and myself. The burning of 10-ton carbon has 12 grams per mole, produces 36.66 tons of CO2. But the burning of coal also generates 10% by weight of fly ash. In other words, 10 tons of coal is producing 1 ton of fly ash and emits 33 tons of CO2. If we take geopolymer cement or a Portland cement that is blended with a 50% fly ash, then we have to add 16.5 tons of CO2 emission to what has been calculated. This seems to be extravagant numbers. They are extravagant numbers compared with what we have been claiming so far, that is 0.2 tons CO2 for 1 ton of geopolymer cement, 16.5. Or for Portland cement, 0.9 ton of CO2 for 1 ton of ordinary Portland cement. But Portland cement experts and Portland cement industry are not aware of these numbers and are asking for more and more fly ash. Why? Because the United Nations Environment Program presented in 2017 in Paris a result of their study on eco-efficient cements, potential economically viable solutions for a low CO2 cement-based materials industry. And this study has been under the directions of these authors, Karen L. Scrivener from École Polytechnique Lausanne in Switzerland, Vanderlei M. John from Polytechnic School, University of Sao Paulo, Brazil, and Elise M. Gardner, former scientific director Lafarge. Scrivener and Gardner have been both scientific advisor at Lafarge, France being one of the biggest Portland cement company in the world. They have a section dedicated to geopolymer cements and alkali activated materials. And I read. These are excerpts. On the resource side, there are major limitations for geopolymer cements. These materials use the same substances, slag and fly ash, as those used to substitute clinker in OPC blends, whose limited availability was discussed in the previous section. So we know that the Portland cement industry, in order to decrease the amount of CO2 that it is emitting, has only one solution: to blend it either with slag or fly ash. Without slag and fly ash, it is unable to cope with the requirement which ask for lower CO2 emission. So this is what is written here. In the case of slag, almost all suitable quality slag is already used in conventional Portland-based cement or concrete, so there is no place, no quality slag available for geopolymer cement. If slag and fly ash are diverted from use in Portland cement-based blends to be used in geopolymer materials, it may be that the CO2 emission per ton of the alkali activated material will be lower, but the CO2 per ton of Portland-based materials will increase due to the lack of slag and fly ash for blending. Therefore, geopolymer cements can only contribute globally to the reduction of CO2 emissions in the sector if they primarily use minerals or industrial byproducts not currently used as clinker substitute in blended cement. In other words, we prohibit the development of geopolymer cement based on fly ash and slag. The slag and fly ash must be only used by Portland. Final remarks. Geopolymer material produced with fly ash and blast furnace slag have low CO2 footprint, but their mitigation potential is dubious, that is, suspicious, unreliable, since they will mostly divert slag and fly ash from Portland cement. So, the strong lobby of Portland cement is working at the United Nations Environmental Programme in order to stop the development of geopolymer cement. But they request more and more fly ash. The fact that the fly ash is used to make building materials is an excuse to increase coal production. Power plants are lobbying the cement and building industry with so-called low CO2 fly ash-based cement. Any development and implementation of fly ash-based cement is supporting the burning of coal in the production of electricity and increasing CO2 emission. Therefore, stop fly ash-based geopolymer cement. Experts are stating that this CO2 does not count because it has already been spent in the production of electricity. But we understand that this production has no future because it is harmful to the global climate. Therefore, the production of fly ash-based cement is not a long-term solution. Fly ash-based cement is supporting the burning of coal and increase global warming. Admittedly, the material is available and sometimes stored in large quantities, so it can be used, but I think it is not suitable for long-term mass production, only for local short-term markets or technical specialties. Therefore, we should stop promoting coal fly ash-based geopolymer cement, and I strongly recommend to replace fly ash with rock-based ferro-sialate geopolymer cement technology. After this strong statement, Geopolymer and Archaeology. We had two topics this year. I already mentioned above the ancient Roman cement, that is our archaeological analogues, and second, the continuation of our project in South America. I already presented last year the results of our study that we carried out in Bolivia at Tiwanaku and Pumapunku. Our study involved the group of megalithic slabs that are the largest among the American continents. It is based on sodium, potassium, calcium, ferro-sialate Geopolymer cement, and these huge slabs provide an answer to the long-term durability of sandstone geopolymer concrete, 1,400 years minimum. So we had discovered that at that site they used two systems, the alkaline system, this is sandstone geopolymer concrete, and method number two, the acidic system for the production of so-called andesite and volcanic stone. Our next project will be in Cusco, in Peru, at Sacsayhuaman, which has blocks that weight up to 350 tons. The problem that we are encountering is that there is practically very few geological and metallurgical data available, and one has practically to carry out the geological and metallurgical survey very carefully on the site, and we need help from local Peruvian scientists for this study. This has been my state of the geopolymer research and development for this year. Take care, and I hope we see you next year, 2021. Same time, same place. Bye-bye. Au revoir.